The scene begins in silence, framed by the wide and lonely expanse of the Martian orbit. Out there, where the faint light of the sun begins to lose its warmth and the cold becomes the natural condition of existence, a stranger slides into view. Not a spacecraft, nor a satellite born of human engineering, but an interstellar traveler whose home lies far beyond the reach of our telescopes. Designated 3I Atlas, it cuts across the orbit of Mars at an astonishing 200,000 miles per hour, a velocity so immense that the very numbers seem to slip away from intuition. Against the black velvet of space, Mars itself becomes a backdrop, a red sentinel illuminated by sunlight, and across its face streaks this silent messenger. No engine drives it, no guidance system plots its trajectory. Its movement is the outcome of unfathomable time and gravity's eternal pull, shaped in some star system that is not our own, ejected by planetary forces we can only imagine. To us, it is a whisper, its appearance brief, almost illusory, a fragment from the beyond that offers itself only once before vanishing again into the galactic night. The mystery it brings is simple yet profound. What is it made of? And where does it come from? Each fleeting photon it reflects toward Earth is a coded message from the deep past, from conditions we have never witnessed, perhaps from chemistry unlike any we have yet catalogued. To scientists watching from observatories on Earth, this encounter is more than an astronomical curiosity. It is a chance to probe the building blocks of other solar systems, to capture in one dim streak of light the physics of creation and destruction, the echoes of starbirth and planetary violence. And as it races past Mars, we cannot help but confront the smallness of our own place, waiting for its secrets to be revealed in time too short and distance too vast. The story of 3I Atlas does not begin in the cold silence of Mars's orbit, but much earlier, in the warm domes and quiet nights of Earth-based telescopes. It was the asteroid terrestrial impact last alert system ATLAS that first caught the moving shadow. Designed to safeguard our planet from near-Earth hazards, the ATLAS telescopes scan wide swaths of sky each night, cataloguing stars, asteroids, comets, and the occasional anomaly. On one such evening, in faint digital frames crowded with thousands of background points, astronomers noticed an object moving faster than expected for a typical comet, its apparent brightness out of step with its trajectory. ATLAS, with its twin telescopes in Hawaii, was not searching for interstellar wanderers that night. It was simply keeping its vigil, guarding against rocks that could one day find Earth. Yet, in those observations, a dot of light began to shift in ways that made experienced eyes pause. The movement was subtle but undeniable. This was no ordinary asteroid bound to the Sun by familiar elliptical chains. Instead, the orbital solutions hinted at something extreme, an orbit that refused to close, a path arcing hyperbolically outward, as though the Sun itself could not hold it. From this first glimpse, urgency spread. In the language of astronomy, nothing travels alone. Every detection invites verification. Alerts traveled across the minor planet centers' circulars, calling the global network of observers to act quickly. Within hours, other surveys turned their eyes to the coordinates: Pan, stars, the Zwicky transient facility, and smaller observatories around the world. The race was on not against the object itself, but against time, for its window of visibility would shrink as quickly as it had opened. In those opening nights of discovery, the mystery deepened. Was this another Oort cloud body, a rogue comet set free by Jupiter's restless tug? Or was it, as calculations began to suggest, a third visitor from beyond our solar system, following in the enigmatic footsteps of Oumuamua and Borisov? The astronomers who first registered its faint trace knew they were at the threshold of something rare. A new messenger had entered the solar system, and with it, a fleeting chance to interrogate the chemistry and physics of worlds that circle other suns. When the first reports of 3I Atlas spread through the astronomical community, the excitement was immediate but cautious. Discovery alone does not make a case. Independent confirmation is the bedrock of science. Observatories across the globe, some automated, others manned by small teams working through the night, rushed to catch the object in their fields of view. Each additional measurement was a new stitch in the fabric of certainty, helping to refine its trajectory against the immense canvas of the sky. The Zwicky Transient Facility in California was among the first to respond, its wide-field camera capable of sweeping vast regions in a single exposure. Soon after, Pan-STARRS atop Haleakala joined in, its sharp imaging power adding clarity to the growing dataset. Together with observatories in the Southern Hemisphere, Chile, South Africa, and Australia, the international net tightened around this mysterious visitor. Each observatory became a relay in a grand choreography, passing the faint dot from one night to the next as Earth turned and the opportunity shifted across longitudes. The Minor Planet Center, MPC, the clearinghouse for such discoveries, collected and collated these measurements. Each position, measured against the fixed stars, reduced the uncertainty in its orbit. Early predictions had left room for ambiguity. Was it truly unbound, or could hidden errors be masquerading as a hyperbolic arc? With each new data point, the veil thinned. The calculated eccentricity surged past 1.0, the unmistakable threshold separating solar system natives from true interstellar wanderers. It was in these confirmations that the object earned its new designation, 3I Atlas, the third recognized interstellar object to pass through our neighborhood. The eye spoke volumes, interstellar, unbound, forever moving outward, never to return. For many astronomers, this was a moment of vindication. The galaxy must be littered with such fragments, flung free from their parent systems. Yet only now, with modern sky surveys running tirelessly and digital pipelines alerting the world in real time, were we beginning to see them. The realization brought more than satisfaction, it brought urgency. Interstellar objects do not linger, their speeds are too great, their light too faint. The observations needed to be swift, coordinated, relentless. And so, the world's astronomers, from vast government-funded telescopes to amateur observers with backyard setups, formed an unspoken alliance. Together, they would track this shard of another world, hoping to decode even a fraction of the story it carried across the dark. With confirmation secured, attention turned to the orbit itself, a slender mathematical arc fitted through nights of astrometric points. At first, the curve was crude, swollen with uncertainty. Could it intersect Earth's path? Could it collide with Mars? Such were the questions whispered in those early days, as crude models left shadows of possibility. The eccentricity shouted hyperbolic, but with only a short baseline, the numbers could dance dangerously. Astronomers knew from experience that hasty calculations can exaggerate risks. The cosmos demands patience. As more measurements accumulated, the fog lifted. Each additional night sharpened the trajectory, drawing its path more cleanly against the gravitational field of the Sunday. The hyperbola remained, unyielding and elegant, but the line bent away from alarm. It would pass cosmically close by the orbit of Mars, yet not within striking range of planet or moon. Earth, too, was safe, its blue arc lying far from this interstellar path. For a time, the world's press flirted with the word hazard. An object traveling at 200,000 miles per hour inspires unease, even if only faintly visible in telescopes. But those fears subsided as the orbital solution tightened, the uncertainties shrinking like a lens coming into focus. Relief replaced anxiety, though not entirely. For the scientific community, the absence of danger was both comfort and frustration. A close brush with Earth would have magnified opportunity, brighter magnitudes, sharper spectra, perhaps even radar echoes. Yet fate had written another script. A pass near Mars, visible but fleeting. The hyperbola itself became a source of wonder. No comet, no asteroid born within the sun's grasp can sustain such a path. Only something born in another system, exiled by distant planetary gravity, can race past us with this unbound freedom. Its sheer velocity, 200,000 miles per hour, relative to Mars, was both a signature and a warning. To capture detail would require relentless coordination. The object would never slow, never circle back. It was a visitor on a one-way journey, curving briefly through our sunlight before vanishing forever into the dark sea between stars. Thus the story sharpened. No impactor, but no long guest either. A shard from alien skies would graze our planetary neighbor and be gone, leaving only a trail of data and a set of riddles too vast to solve in one pass. The discovery had been made, the orbit secured, and the alarm dismissed. What remained was the fleeting chance to observe. In astronomy, windows of opportunity are fragile things, opening for nights or weeks before closing again for centuries, or in this case, for eternity. 3. Atlas would not tarry. Its velocity meant that within months it would sink into invisibility, fading below the reach of even the world's largest telescopes. The geometry of observation, Sun, Earth, Mars, and the traveler itself would dictate who could see and for how long. As the object approached its perihelion and Mars-side flyby, scientists raced to schedule their instruments. Time on telescopes is not given lightly. Every night is contested among projects spanning the cosmos. Yet here, urgency worked in their favor. To witness only the third recognized interstellar visitor was to stand at a rare frontier, and committees bent rules to grant priority. Exposure times were carefully calculated. Filters were chosen to balance sensitivity against faintness. Should they aim for broadband colors to reveal surface hues, or narrowband filters tuned to gases that might escape its crust? Each choice was a gamble, because the visitor would grant so few photons, so few opportunities. The brightness curve narrowed the field further. At best, 3. Atlas would remain observable for weeks in optimal conditions. Clouds, moonlight, and atmospheric turbulence, all the earthly nuisances of astronomy, became threats to irreplaceable data. Scientists coordinated globally, handing the target across latitudes and longitudes so that as the planet rotated, another eye would open, another camera would hum. In this dance, cooperation was necessity. No single observatory could capture the whole passage. Amid this logistical choreography lay the deeper truth. Every photon mattered. Each captured streak of light was not merely brightness, but information encoded by the surface chemistry and history of a fragment that had wandered the galaxy for perhaps hundreds of millions of years. And each photon lost, scattered by clouds, drowned by moonlight, was a secret carried beyond recovery. The clock ticked relentlessly. The window was brief, measured in nights, not years. Humanity had to be ready, because 3 Atlas would not wait. Why, among all the objects drifting past the planets, did this one ignite such astonishment? The answer lay not only in its foreignness, but in its defiance of expectation. Humanity had seen interstellar visitors before. Oumuamua in 2017, elongated, tumbling, and silent, followed 2 years later by Borisov, a comet in every classical sense. These two pioneers had sketched out the boundaries of possibility: a comet with a coma and a shard without one. Between them, astronomers imagined a spectrum of behaviors. Yet 3 Atlas, racing past Mars, appeared to redraw that spectrum in unsettling ways. Its speed was not unprecedented, but was remarkable. 200,000 miles per hour relative to Mars meant that this fragment had not been born anywhere nearby. It carried the velocity of a past exile, hurled by the gravity of giants in another star system. Its brightness was strange as well, too faint for its distance, as though its surface swallowed light rather than scattering it. In images, it betrayed no dramatic tail, no shining halo of gas. It was neither the flamboyant comet that Borisov had been, nor entirely the silent enigma of Oumuamua. It sat uneasily between categories, showing hints of each but satisfying neither. For planetary scientists, this ambiguity was as thrilling as it was frustrating. The neat textbook divisions, asteroid, comet, dormant core, were suddenly porous. Here was an object that seemed to reject classification, to insist that our categories were provincial. If star systems across the galaxy eject fragments of this kind, then the very building blocks of planets may be more diverse than our local examples suggest. What stunned observers most was the reminder of scale. The galaxy is vast beyond comprehension, yet in less than a decade humanity had detected not one but 3 messengers crossing our path. This was not coincidence. It was revelation. The solar system, long thought to be an isolated stage, is in fact an open harbour through which strangers drift. 3I Atlas, in its strangeness, announced that the cosmic traffic is richer, stranger, and faster than we had dared to hope. The more astronomers examined 3I Atlas, the more it seemed to bend the rules of familiarity without shattering them outright. Its path obeyed Newton's laws perfectly, a hyperbolic arc dictated by gravity, its motion calculable to exquisite precision once enough data had been gathered. No violation of celestial mechanics lurked in its trajectory. The sun's pull shaped its passage, and Mars, for all its proximity, exerted no measurable detour. On this level, physics held firm. Yet when scientists looked beyond the orbit to the physical character of the object, the categories began to blur. Was it solid rock, like the asteroids of our own system? Was it volatile rich, a comet's icy core long dormant until warmed? Photometric data hinted at a surface darker than charcoal, absorbing rather than reflecting, yet the absence of a coma made it resistant to classification as a comet. At times, subtle deviations in its measured position sparked speculation of faint outgassing or a whisper of radiation pressure phenomena reminiscent of Oumuamua's unexplained accelerations. These suggestions unsettled researchers. They did not break physics, but they strained the models built to describe small bodies. How could something so faint, so seemingly inert, display behaviors hinting at internal activity? If dust or gases escaped, they did so invisibly, hidden from the instruments that would normally betray such emissions. If no activity existed, then other forces, perhaps an unusual geometry, perhaps porosity beyond any asteroid yet seen, would need to be invoked. In this tension lay the beauty of the moment. Science thrives not on tidy answers, but on anomalies that resist explanation. 3I Atlas became a mirror held up to our assumptions, exposing the gaps in how we classify, predict, and understand. The rules of motion remained intact, but the rules of identity trembled. It was neither fully comet nor wholly asteroid, neither fully dormant nor clearly active. It was something between, something that forced the lexicon of astronomy to stretch and flex in search of words that did not yet exist. The universe had not betrayed its order, but it had reminded us that our categories are provisional, our definitions provincial. In the passage of this interstellar shard, humanity glimpsed the humility required to study a cosmos that forever refuses to fit into boxes of our making. The orbit of 3I Atlas, unbound and unyielding, unfolded as a reminder of the deeper architecture of reality. To most observers, a hyperbolic path is merely the geometry of escape, a body arriving from infinity, swinging around the sun, then vanishing again into the black. But to physicists steeped in Einstein's insights, the trajectory was more than geometry. It was a geodesic, a line drawn not across space but through spacetime, curved by the immense presence of the Sunday. In this view, the object was not deflected in the crude sense of Newtonian mechanics. It was following the straightest path possible in a universe where straight lines are bent by mass. The Sun, 100 times the Earth's diameter and vast in its invisible reach, sculpted a valley in the fabric of space-time. 3I Atlas, for all its alien provenance, could not resist that contour. It fell inward, sped up, and curved outward again, all without breaking a single law of relativity. Its arc was a silent testimony to the order of the cosmos, a demonstration that Einstein's century-old equations still govern even messengers from beyond the stars. And yet, within this order, a sense of fragility lingers. The mathematics explains the motion, but not the origin. The hyperbola is precise, but indifferent to the object's story. From what star was it cast? By what planetary violence was it expelled? Those questions lie beyond the equations of relativity. They belong instead to the human effort to stitch narrative to fact, to place the shard within a cosmic biography. As the object slid through the sun's gravity well, it illuminated another truth, that our solar system is not a closed sanctuary. Space is porous, its boundaries crossed by fragments from elsewhere. Each such visitor is a punctuation mark written into the solar narrative by forces far away. The arc of 3I Atlas, therefore, was not only a path through space-time but a sentence in a story written across the galaxy, a sentence brief, enigmatic, and waiting to be interpreted before it fades into silence again. As 3I Atlas drew near Mars's orbit, geometry itself became an ally to science. The red planet was not a participant in the drama, its mass too small, its gravity too weak to deflect the traveler, but it played the role of backdrop, a luminous stage against which subtle phenomena might be revealed. From Earth, the alignment offered rare phase angles, configurations where sunlight, the object, and the observer formed geometries capable of teasing out hidden truths. This was not merely a matter of brightness. When the sun shone from behind, the scattering of light across dust or ice grains could be amplified, revealing faint halos invisible at other times. Forward scattering, as physicists call it, turns the tiniest particles into temporary lanterns. If 3I Atlas carried a veil of dust, or if sublimation lifted molecules into space, these geometries with Mars in the background could betray it. For planetary scientists, this opportunity was tantalizing. Most comets are studied at angles dictated by chance, their tails and comae viewed from positions less than ideal. But here, the interstellar shards close past to Mars produced conditions that would rarely repeat, the red planet acting as a canvas, its reflected light and contrasting color providing both a measuring stick and a filter. Instruments tuned to capture the faintest traces of forward scattered light prepared to seek signatures at the very edge of detectability. There was symbolism too in the setting. Mars, long the subject of human fascination, the cradle of imagined canals, and the target of robotic explorers, now became a silent collaborator in a cosmic experiment. As the dust-red horizon of the planet swept beneath this alien shard, astronomers envisioned the possibility of Martian orbiters themselves, catching glimpses, amplifying the global effort. The chance was brief, measured in hours and days rather than months. Yet in those fleeting alignments, the universe granted science a favor, a cosmic alignment where one world framed another, and in the space between, a fragment from the galaxy revealed its nature through the quiet physics of light. With geometry on their side, astronomers turned their focus to the light itself, not the broad strokes of orbit, but the delicate flicker that betrayed rotation and shape. Every small body spins, and in its spin lies a story of collisions survived, of ejection from a parent system, of time adrift beneath cosmic rays. For 3I Atlas, the only way to measure that spin was through light curves, the subtle waxing and waning of brightness as irregular surfaces caught and released sunlight. Telescopes around the world began to collect these curves, each point a fragile photon captured across the dark. When assembled, the data resembled a pulse, brightness rising, falling, then rising again. The amplitude of this flicker hinted at elongation, perhaps a shard stretched like a spindle or a fragment flattened like a disk. The periodicity suggested whether it rotated smoothly or tumbled chaotically through space, as Oumuamua had done. In those curves lay the possibility of reconstructing a silhouette to glimpse the body's outline without ever approaching it. Yet the light was faint, and the cadence demanded speed. To catch a rotation period measured in hours, exposures had to be short enough to resolve variation, yet long enough to gather enough photons for certainty. Astronomers balanced on the knife edge of signal and noise, repeating observations through nights of poor seeing, clouds, and instrument limits. Out of this persistence came patterns, flickers that suggested not a sphere, not a neat pebble, but something fractured and asymmetric. The curves whispered of fragility. A high amplitude meant extremes, one face bright, another dark, consistent with an object porous, riddled with voids, perhaps a fragment from a catastrophic breakup. If so, it carried scars from violent origins, a planetary encounter, a collisional ejection, a long journey battered by micrometeorites. And every flicker was a reminder that what crossed our sky was not theoretical but physical. A shard of rock and ice, tumbling silently, indifferent to the eyes that strained to read its secrets. Once the pulse of light curves suggested a tumbling shard, the next question turned to its skin, the spectral fingerprint of its surface. Astronomers switched from measuring brightness to measuring color, spreading the light into bands to search for clues about chemistry. Even in faint photons, patterns emerge. Slopes that redden or blue with wavelength, subtle dips where molecules absorb, hints of ice or organic compounds clinging to the crust. For 3I Atlas, the colors were muted, neither bright like icy comets nor neutral like many asteroids. Instead, its spectrum tilted slightly toward the red, a hue reminiscent of surfaces baked by cosmic rays. This was not surprising. Objects adrift in interstellar space for millions of years endure a relentless bombardment of high-energy particles. Over time, their surfaces develop irradiation mantles, dark crusts rich in complex organics, tholins forged in the crucible of galactic radiation. These layers conceal the fresher interior, protecting volatile ices below but hiding them from our eyes. The faint slope raised questions. Was this object a cousin of outer solar system bodies like Kuiper belt objects, their surfaces similarly reddened and inert? Or was it something altogether different, a fragment from a planetary system born in conditions we cannot replicate? Astronomers knew they were looking at the faintest hints, interpreting curves with caution, aware that small errors in calibration or atmospheric interference could mimic or erase the signature of true chemistry. Yet even with uncertainty, the data aligned with expectation. Interstellar travelers are not pristine. They are aged wanderers, their outer layers scarred and altered by eons of radiation. The reddish tint, the dark reflectivity, the absence of bright ice together, they painted a picture of a fragment hardened by exile. But beneath that crust, perhaps still intact, could lie volatile ices untouched since the moment of ejection. If only the object could be approached, drilled, sampled. Instead, humanity could only stare from afar, inferring chemistry from colors faint as whispers, knowing that every night it grew dimmer. The skin of 3I Atlas told a tale, but not the whole. Its surface bore the scars of time between stars. Its heart remained veiled. If the visible spectrum whispered of surfaces and organics, the infrared promised to speak more directly of size, temperature, and hidden ices. In visible light, brightness is deceptive. A small, shiny pebble can look the same as a vast, dark boulder. Only thermal emission, the faint glow of warmth radiated away, can disentangle reflectivity from true dimension. For 3I Atlas, infrared eyes became indispensable. Instruments tuned to longer wavelengths, NASA's NEOWISE telescope, ground-based detectors on Mauna Kea, and Europe's infrared arrays strained to capture the heat signature of an object impossibly faint. At Mars's distance, under the thin sunlight of the outer system, the shard's temperature hovered near the freezing point of nitrogen. Its infrared glow was little more than a whisper in the dark. Yet even a handful of photons could reveal much. By comparing thermal flux with reflected light, astronomers could estimate its albedo, its diameter, and the roughness of its surface. Was it a glossy shard of ice, or a blackened lump that swallowed sunlight? Data suggested a body small but not trivial, hundreds of meters across, likely elongated. Its surface was darker than asphalt, radiating weakly. Crucially, no excess thermal emission betrayed active sublimation. Unlike Borisov, with its clear jets of carbon monoxide, 3I Atlas remained stubbornly quiet. But silence itself was a message. It told of a crust thick enough, or an orbit through interstellar cold long enough to suppress activity. If volatiles lingered inside, they remained locked behind a shell of irradiated dust and carbon. Infrared spectra probed deeper still. Small bumps and troughs hinted at silicate minerals, the stuff of rocky worlds. Other features suggested amorphous ices, their bonds stretched thin by cosmic rays. Though faint and ambiguous, these fingerprints tied 3I Atlas to a lineage, not exotic alien matter, but familiar ingredients reassembled under foreign suns. In the red light, invisible to human eyes, the interstellar shard spoke of paradox. It was both alien and known, both ordinary rock and extraordinary traveler. The infrared glow was faint, soon to vanish into cosmic night, but in it lay the story of how planets and stars throw fragments into eternity, and how, by chance, one fragment passed our way. If ground-based telescopes and orbital observatories strained to capture fragments of light, a far greater eye loomed in the collective imagination, the James Webb Space Telescope. Though never built to chase faint, fast-moving targets, Webb possessed a sensitivity unrivaled in human history, and astronomers wondered if this interstellar shard could be snared by its golden mirrors. To that end, proposals for a target of opportunity were drafted, invoking the telescope's ability to interrupt its scheduled program when cosmic events of rare urgency demanded it. Time was not on their side. Webb's field of regard, restricted by the need to shield its instruments from the sun, meant that 3I Atlas would pass only briefly through its view. The calculations were merciless. A handful of nights, perhaps even a single window, when its faint signal would align with Webb's gaze. Within that fleeting moment lay the chance to probe not just color and brightness, but molecular composition itself. For Webb's instruments, finely tuned to the mid-infrared, could dissect the spectrum of this visitor and reveal the gases and solids it carried. If carbon monoxide or carbon dioxide sublimated from its surface, Webb could see the faint lines of those molecules, fingerprints, etched in light. If water ice sublimated in trace amounts, Webb could detect it, even where ground-based instruments failed. More tantalizing still, Webb could test for the subtle features of organics: carbon-hydrogen bonds, silicate vibrations, spectral signatures that hinted at chemistry born in alien nurseries. Yet the ambition was tempered by reality. Tracking an object moving at nearly 200,000 miles per hour relative to Mars posed a challenge even to Webb's precision systems. The risk of missing the faint target was real, and should it fail, the loss would be permanent. There would be no second chance. Still, astronomers dared. The possibility of capturing the first true infrared spectrum of an interstellar traveler, with detail beyond Oumuamua and Borisov, justified the gamble. If Webb succeeded, humanity would hold not just an image but a chemical story, written in the language of photons from a fragment born around another star. And if it failed, the effort itself would stand as testimony to the urgency and fragility of science pursued at the very edge of possibility. While Earth-based telescopes strained against atmosphere and Webb awaited its fleeting chance, another possibility stirred interest: the silent instruments already orbiting Mars. Though designed to study the red planet itself, spacecraft like the Mars Reconnaissance Orbiter, MAVEN, and Mars Express each carried eyes that, in principle, could look outward. Their vantage point was extraordinary, perched near the very stage where 3I Atlas would sweep past, free from the distortions of Earth's atmosphere, far closer than any telescope on the ground. Scientists debated the feasibility. Orbital cameras were built for surface imaging, not for chasing interstellar shards across the heavens. Pointing constraints, limited fields of view, and the sheer speed of the object made capture uncertain. Yet the idea lingered. Could one of these orbiters, in the right moment, glance away from Mars and glimpse the faint visitor? If so, even a handful of exposures could yield unprecedented geometry, direct imaging of the object against the backdrop of stars at phase angles impossible from Earth. MAVEN, with its focus on Mars's atmosphere and solar wind, offered another prospect. If 3I Atlas carried even the faintest tail of ions or dust, instruments tuned to plasma interactions might detect perturbations. A dust grain or molecular trace, invisible from Earth, could betray itself in data gathered almost incidentally by machines designed for another purpose. The chance was slim, but the potential reward vast: to sample interstellar material not just with photons, but through the subtle physics of interaction near a planetary neighbor. For mission teams, the prospect embodied both daring and restraint. Spacecraft operations are cautious, risk-averse. Instruments cannot be repointed on whim. But in meetings and proposals, scientists made their case. Mars, once a symbol of human longing, could now serve as an astronomical outpost, extending humanity's reach beyond Earth. If one orbiter caught even a trace of this shard, it would mark a first, a planetary mission doubling as witness to an interstellar visitor. Whether successful or not, the attempt reflected a growing vision that exploration need not be limited to planned targets. Sometimes the cosmos brings gifts unannounced, and the true measure of science is whether we are ready to receive them. Among the many tools deployed in the pursuit of 3I Atlas, one was both subtle and profound: polarimetry. Unlike ordinary photometry, which measures brightness, polarimetry measures the orientation of light waves after scattering from a surface or through dust. To the untrained eye, light is just illumination, but to astronomers, its polarization reveals the size, texture, and even the porosity of the particles that scatter it. For a faint interstellar traveler, this technique offered a way to glimpse what no telescope could resolve: the microphysics of its dust and crust. When light from the sun struck 3I Atlas, some of it scattered at angles that revealed whether the surface was smooth, glassy, or cloaked in fine particulate. Comets within our system display strong polarization signatures, especially when their comae are rich with micron-sized grains. Asteroids, by contrast, reflect more neutrally, their bare rock scattering in less organized patterns. 3I Atlas, sliding past Mars, could lean toward either category or invent an entirely new one. Global teams mounted polarimetric campaigns, chasing the object with filters and analyzers designed to pass light into vectors. The results were tentative, fragile, built from photons, almost too few to count. Yet even so, patterns emerged. A modest but measurable polarization, higher than bare rock would suggest, lower than the flamboyant plumes of an active comet. This middle ground again placed the object in limbo, as if deliberately resisting easy categorization. Perhaps its crust shed a thin haze of dust, invisible in images but detectable in the polarization curve. Or perhaps its surface, porous and fractured, mimicked the scattering behavior of dust without releasing any into space. To interpret such curves required models of grain physics, simulations of how fractured silicates, carbonized organics, or icy shards scatter light at different angles. Each model offered a possible truth, each more intriguing than the last. In every case, the data spoke of complexity. This was not a monolithic rock, but a textured traveler, shaped by processes beyond our solar system. In the language of polarized light, 3I Atlas whispered a quiet revelation. The galaxy does not make its fragments simple. Even in the smallest details, the alien shard bore the signature of diversity, complexity, and histories we have only begun to imagine. For a brief moment, hope turned toward radar, the technique that had mapped near-Earth asteroids in exquisite detail, resolving boulders and craters across millions of kilometers. Planetary radar, using the mighty transmitters of Arecibo in its prime or Goldstone today, had long been the gold standard for characterizing small bodies. Could 3I Atlas, racing past the orbit of Mars, be illuminated by such beams, its echo returning across the void with the crispness of a fingerprint? The answer, though pursued with determination, was sobering. Radar depends on both distance and size, and here the odds conspired against us. 3I Atlas was small, faint, and fleeting, its closest approach far beyond the comfortable range of Earth's transmitters. Even at full power, the signal-to-noise ratio fell orders of magnitude below usability. What radar had revealed about near-Earth asteroids, their shapes, spin states, even binary companions would remain hidden in this case. Yet the very consideration revealed something profound about our limitations. For all our technology, for all our ingenuity, there are boundaries set by physics and distance that no enthusiasm can cross. Radar beams spread, weaken, and fade. The object, too small and too far, could not be grasped by radio. Humanity's reach, for now, extended only through photons, the light reflected or emitted from its alien surface. Still, the attempt was not in vain. By running calculations, by testing system limits, scientists gained insight into what would be required next time. A more powerful transmitter? A space-based radar outpost, free from Earth's constraints? Such questions began to circulate. Each interstellar visitor sharpened the blueprint for future tools, teaching by negation what could and could not be done. So 3I Atlas remained beyond radar's embrace. It left no echoes bouncing back to Earth, no crisp silhouettes rendered in microwave hues. Instead, it demanded humility. The object reminded us that the universe is vast, that our instruments are young, and that sometimes the cosmos offers riddles we must accept in fragments, knowing that complete answers are still beyond our grasp. As astronomers tracked 3I Atlas with exquisite precision, a subtler question emerged. Was its motion truly perfect? Or did something invisible nudge it ever so slightly off the clean hyperbola predicted by Newton and Einstein? Such non-gravitational accelerations, while tiny, had already haunted the study of Oumuamua, whose trajectory bent more than gravity alone could explain. The cause of that deviation remains unsettled, oscillating between models of exotic outgassing, evaporating hydrogen ice, nitrogen shards, and even ultraporous structures susceptible to sunlight's pressure. For 3I Atlas, the search began again. Each astrometric point, each measured position against the grid of background stars became a test. If the orbit could not be reconciled with pure gravity, then another force was at play. The usual culprit would be outgassing, jets of sublimating volatiles imparting thrust. But where was the coma? Images showed no obvious halo, no streaming tail. If gases escaped, they did so invisibly, at levels so faint they eluded detection, yet still left fingerprints in the path. Other possibilities stirred debate. Could radiation pressure alone explain a deviation, pushing against a body so thin and porous that sunlight acted like wind against a sail? If so, 3I Atlas would have to be an astonishing structure, an aggregate of dust and void, fragile enough to bend to photons, yet cohesive enough to survive ejection from another star system and the long interstellar voyage. The data, as always, refused to yield easily. Some fits suggested minute accelerations, others fell within error margins. Teams scrutinized every potential source of bias: calibration, atmosphere, instrumental drift. The uncertainty itself became part of the narrative, echoing the debates of Oumuamua but set in a new context. If non-gravitational forces were present, they were subtle, muted, perhaps buried under a crust hardened by cosmic rays. In chasing these nudges, astronomers sought not just to explain one orbit, but to illuminate a broader truth. Each interstellar shard, by revealing or denying such accelerations, helps define what kinds of bodies roam between the stars. Are they icy seeds, rocky splinters, porous veils? The answer hides in these deviations, tiny whispers in the mathematics of motion that speak of internal structure, hidden volatiles, and the physics of alien worlds. The question of shape, teased from the dance of light curves, became an obsession. For 3I Atlas, no telescope would ever resolve its body directly. It was too small, too distant, too fast. But the flicker of brightness, when modeled with care, could be inverted into a form, a shadow geometry reconstructed from the rhythm of sunlight. Teams fed the photometric data into algorithms of light curve inversion, peeling back uncertainty to imagine the silhouette of this interstellar shard. The results were evocative. Some solutions suggested a spindle, long and thin, rotating on its axis like a cosmic needle. Others pointed toward a flattened, pancake-like shard, its surface catching and losing light in wide sweeps. The amplitude of the light curve, unusually high, made both options plausible. What was clear was that this was no simple sphere, no quiet pebble drifting through the dark. It was an irregular fragment, shaped by violence and exile. Rotation models added further intrigue. Some data hinted at a complex spin state, not a clean single-axis rotation, but a tumbling motion, chaotic, unresolved, the legacy of past collisions or the violent ejection from its parent system. This tumbling would cause internal stresses, perhaps even fracturing the body over eons of travel. To persist for millions of years despite such motion suggested a structure neither wholly fragile nor fully solid, but somewhere between a loosely bound aggregate or a fractured monolith hardened by cosmic rays. The implications stretched wider. Shape dictated how sunlight heated the surface, how ices sublimated, how dust might be released. It also framed theories of ejection. Was this a splinter chipped off a larger body, or the survivor of a catastrophic collision between protoplanets? Its form was both a relic and a clue, a frozen record of processes from another solar system. Though models diverged, one truth remained. 3. I Atlas was extreme. Its geometry, like its orbit, refused to be ordinary. In its shadowy outline, inferred from distant flickers, lay a story of shattering forces and endurance across the dark sea of interstellar space, a story humanity could glimpse only in silhouette, never in full. If its shape hinted at violence and survival, its chemistry promised to speak of origins. For astronomers, the dream was to capture the spectral fingerprints of molecules, the delicate absorption lines that reveal composition. Every element and compound leaves its mark, whether water, ice, carbon monoxide, carbon dioxide, or the complex organics that build prebiotic chemistry. To decode 3I Atlas was to peek into the pantry of another planetary system. Spectrographs were turned toward it, their prisms and gratings spreading faint photons into rainbow bands. In the data, scientists searched for the telltale signatures of volatile gases. If carbon monoxide appeared, it would hint at storage in an icy, Pluto-like body. If carbon dioxide or water revealed themselves, the shard might once have been part of a cometary shell, now stripped and scarred. If silicates dominated, then perhaps it was rocky, a splinter of a planetesimal hardened in the fire of alien starbirth. The results were tantalizing, though frustratingly faint. A handful of features suggested weak absorption by carbon-bearing compounds, possible organics. Some slopes resembled those of Kuiper belt objects, coated in tholins forged by radiation. Others hinted at the spectral hum of silicates, whispering of rock beneath the crust. Yet nothing was unambiguous. The object was too faint, its window too brief, the interference of Earth's atmosphere too stubborn. Still, the possibilities painted vivid scenarios. Perhaps this was a fragment of an exo-Pluto, its nitrogen and methane long lost, its surface reddened and carbonized. Perhaps it was a devolatilized comet, its ices burned away in its native system before ejection. Or perhaps it was something stranger, a shard of rocky mantle or crust, broken loose in the early chaos of planet formation. Each option carried implications for the diversity of planetary systems, each a new chapter in the galactic story of how worlds assemble and fracture. Though incomplete, the chemical hints carried weight. They showed that the visitor was not alien in the sense of being unrecognizable. Its building blocks were familiar carbon, oxygen, silicates, yet arranged and processed beyond our sun's reach. In those faint spectra, humanity glimpsed kinship. The galaxy's planets and debris may differ, but they are written in the same cosmic language of matter. While photons revealed chemistry, another line of inquiry probed the age of 3I Atlas, not in years counted since discovery, but in cosmic time etched into its surface. Every object wandering through the interstellar medium is bombarded by high-energy particles, cosmic rays, fast protons, and heavy nuclei that pummel its crust. Over millions of years, these particles alter the chemistry, implant isotopes, and erode volatiles. In essence, they function as clocks, leaving behind markers of how long a body has drifted between stars. Scientists sought to measure this cosmic ray exposure age through subtle cues in its spectrum. The reddened slope, the darkened albedo, the possible tholin coating all suggested long exposure, perhaps tens or hundreds of millions of years. In theory, if material from such a body were ever captured, isotopic ratios of noble gases could offer precise dating. Without a sample, only inference was possible. But even inference told a story. 3I Atlas was no newborn shard. It had sailed the interstellar ocean for epochs far longer than human civilization has existed. Its survival raised questions about durability. How could a body so small, perhaps only a few hundred meters across, endure the hazards of cosmic radiation, micrometeorite impacts, and thermal cycling for such lengths of time? One answer lay in its crust, hardened by irradiation into a protective shell. Beneath, volatile rich layers could remain sealed, shielded from the ravages of space. Another answer lay in chance. Many such fragments must be destroyed in transit, but a few survive, statistical outliers preserved long enough to wander into another system's light. The cosmic ray record also hinted at violence. To be cast into interstellar space, 3I Atlas must once have been part of a larger world, ejected by gravitational encounters or collisional cataclysm. The clock that began ticking at ejection thus measured not just age but trauma, the instant when this fragment was torn free and sent adrift. In contemplating its exposure age, astronomers saw more than numbers. They saw time itself written into matter. Here was a shard, older than nations, older than humanity, older even than many stars we see in the sky. To study it was to brush against the immensity of cosmic history, encapsulated in a fragment that, for a moment, brushed close to Mars. If exposure ages told of survival, orbital mechanics pointed toward birthplace. Astronomers attempted the delicate work of tracing 3I Atlas back through time, running its orbit in reverse to guess at the region of the galaxy from which it came. Such exercises are fraught, gravity's touch is cumulative, and the uncertainties grow enormous across millions of years, but even broad strokes carry meaning. The velocity vector was the first clue. Its direction relative to the Sun suggested no clear connection to known stellar neighbors. This was not debris freshly shed by Proxima Centauri or any nearby star. Instead, its inbound trajectory pointed vaguely toward regions of the galactic disk, teeming with young stars and giant planets. Simulations showed that the most likely culprits were outer planetary systems, where migrating gas giants sling debris outward with tremendous force. Over time, countless fragments escape, seeding the interstellar medium with shards like this one. Though the exact star could not be identified, statistical studies helped. The number of expected interstellar objects, extrapolated from the discoveries of Oumuamua, Borisov, and now Atlas, suggested that nearly every planetary system must eject such fragments. The galaxy, then, is not a quiet collection of isolated stars, but a dynamic ecosystem constantly exchanging matter. Our solar system has surely shed its own debris into the void, and now we witness the reciprocal, a shard from elsewhere passing briefly through our light. The birthplace, therefore, was less a single star than a population, perhaps a system with icy outer bodies, perhaps a young cluster where gravitational jostling was fierce. Ejection required violence, but not rarity. It was the inevitable byproduct of planet formation. Each interstellar traveler carries with it the signature of that origin, not in its orbit alone, but in its chemistry, spin, and scarred surface. To trace 3I Atlas backward was to imagine it as part of a planetary nursery, once warmed by a distant sun, perhaps orbiting alongside other planetesimals before a gravitational encounter cast it into exile. Now, it drifted through our solar system as a solitary witness, carrying in its silence the memory of a star it would never see again. Once the question of origin was raised, theorists turned to the mechanics of exile. How does a fragment like 3I Atlas become unbound from its home star and flung into the galactic sea? Planetary dynamics offered the likely answers, each scenario violent in its own way. The most common suspect was giant planets. In many young systems, gas giants migrate inward and outward, their gravity scattering smaller bodies like pebbles in a storm. A close encounter can impart enough energy to fling a planetesimal beyond escape velocity, hurling it into interstellar space. Over the lifetime of a system, billions of such encounters may occur, ensuring that shards like 3I Atlas are not exceptions but inevitabilities. Another possibility lay in stellar encounters. Stars are born in clusters, packed far closer than they are today. In those first tens of millions of years, neighboring stars pass near one another, their tidal pulls disturbing the outer disks of comets and planetesimals. A fragment nudged at the right moment could find itself cast outward, never to return. Over time, as clusters dissolve and stars drift apart, these exiles disperse into the galaxy, silent relics of long-dispersed nurseries. Collisions also offered a route. If planetesimals collided violently in a crowded disk, fragments might be ejected at extraordinary speeds, some bound, others free. A shard like 3I Atlas could be the survivor of such a cataclysm, a splinter from a larger body shattered in the heat of formation. Its irregular shape and tumbling rotation hinted at just such a traumatic birth. Each mechanism painted a slightly different story. A gas giant sling might leave behind volatile-rich comets. A stellar encounter might strip icy belts wholesale. A collision might create jagged fragments of rock. By comparing shape, spectrum, and motion, astronomers tried to deduce which history best fit the data. The conclusion, tentative but compelling, was that 3I Atlas was no accident. It was part of a galactic process, a steady rain of fragments exchanged among stars. Its ejection was not rare but routine, part of the violent churn that accompanies every act of planetary creation. In this sense, its passage near Mars was a gift not just of chance, but of inevitability. The galaxy is full of such wanderers, and one by one, they will pass our way. As models of ejection multiplied, so too did more speculative voices. Could 3I Atlas be something fundamentally exotic, composed not of ordinary ice and rock, but of unusual matter rarely preserved in planetary systems? The temptation to wander beyond the conservative was strong, for the object's ambiguities left room for imagination. Some scientists revisited the nitrogen ice hypothesis, proposed for Oumuamua, that it could be a shard of a Pluto-like world, its nitrogen surface eroded by cosmic rays until only a sliver remained. Others considered hydrogen ice, fantastically volatile, yet capable of explaining strange accelerations, though skeptics noted that hydrogen would scarcely survive interstellar travel. Carbon monoxide and carbon dioxide ices seemed more plausible, able to endure long drifts and release faint thrust when warmed by sunlight. Then there was the possibility of ultraporous aggregates, bodies so fluffy and fragile that radiation pressure could nudge them. Such objects, if they existed, would resemble cosmic aerogel, tenuous webs of dust grains bound together in barely cohesive clouds. Their existence would force a reconsideration of how planetesimals assemble and fracture, raising questions about stability and survival over galactic timescales. More exotic still were whispers of non-natural explanations, though most scientists treated them with caution. Could such a fragment be technological, a derelict from some ancient civilization? Oumuamua's puzzling acceleration had once sparked such speculation. For 3I Atlas, however, no evidence pointed that way. No unusual reflections, no radio signals, no anomalous structure beyond what natural processes might explain. Yet even the dismissal carried meaning. Each interstellar visitor forced humanity to test its readiness to distinguish the natural from the artificial, sharpening the rigor with which we approach extraordinary claims. Ultimately, the consensus leaned toward the ordinary in the cosmic sense, which is to say, extraordinary for us. Volatile ices, rocky silicates, irradiated organics. These were the likely ingredients, but the very act of considering the strange was valuable. It reminded the scientific community that discovery sits at the boundary of knowledge, where the familiar shades into the unknown. 3. I-Atlas may prove conservative in composition, yet its presence alone demonstrated that the galaxy's chemistry is not confined to our small neighborhood. Even if it were merely a dark shard of ice and dust, it was an emissary from alien worlds, matter from another sun, placed before our eyes. To place 3I Atlas in context, astronomers inevitably looked back to the two wanderers that came before it, 1I Oumuamua and 2I Borisov. Each had rewritten assumptions in its own way, and together they formed a sparse but powerful lineage against which this third visitor could be compared. Oumuamua, discovered in 2017, had startled the world. Small, faint, elongated, and accelerating without a visible coma, it became the archetype of mystery, its origin debated, its nature unresolved. Borisov, found in 2019, was the opposite, a textbook comet in appearance, flaring with gas and dust as it approached the sun, behaving exactly as a frozen body should. Between these two extremes, the scientific imagination stretched. Some interstellar visitors would be rocky shards, others icy comets. The spectrum seemed complete. Yet 3I Atlas unsettled that tidy division. It displayed hints of both and commitments to neither. No flamboyant tail, but no silence in its data either. No obvious accelerations, but no guarantee of purely inert motion. Its spectral colors were ambiguous, its shape extreme. In some respects, it mirrored Oumuamua's enigma. In others, it echoed Borisov's familiarity. It stood between categories, as though to remind us that our sample of 3 was still far too small to define what typical means. This comparison revealed something profound. The diversity of interstellar debris may exceed even the diversity within our own solar system. Just as Earth, Mars, comets, and asteroids form a family of wildly different bodies orbiting one star, so too the galaxy must teem with fragments representing countless evolutionary histories. One star ejects icy comets, another rocky splinters, another fragile aggregates, another nitrogen-clad shards. The traffic between systems becomes a mosaic of origins, a living record of planetary processes far beyond our sight. In this light, 3I Atlas was not an outlier, but a bridge. It connected the mystery of Oumuamua with the clarity of Borisov, showing that the truth lies not in extremes, but in a continuum. Each new object shifts the balance, expands the map, and forces science to redraw its expectations. And so, in the faint light of 3I Atlas, astronomers saw less an anomaly than a promise that many more kinds of travelers await discovery, each carrying its own message from the stars. Beyond questions of shape and chemistry lay an even deeper implication. What if interstellar fragments like 3I Atlas carried not just rock and ice, but the very seeds of life? The idea, known as Panspermia, has long lingered on the fringes of astrophysics, suggesting that the ingredients for biology, amino acids, complex organics, even microbes might ride between stars on comets, asteroids, or dust grains. If true, then every interstellar visitor is not merely geological but biological, a courier of potential beginnings. Laboratory experiments on Earth have shown that amino acids can form under harsh cosmic conditions, forged in icy mantles bombarded by radiation. Spacecraft missions to comets within our system, like Rosetta at 67P Churyumov-Gerasimenko, have confirmed the presence of such organics. Meteorites fallen to Earth have carried complex carbon chains older than our planet itself. These findings make it plausible, even likely, that 3I Atlas II could harbor prebiotic chemistry. The prospect is breathtaking. Imagine a shard born around another star, carrying molecules that might resemble those that once seeded Earth's oceans. Its journey could have spanned hundreds of millions of years, through stellar winds, supernova shockwaves, and the cold void. Its surface, irradiated and scarred, might hide within it pockets of material shielded from destruction. Within those pockets could be chains of carbon and hydrogen, nucleobases, or other precursors to life. Of course, caution dominates the scientific mind. No evidence suggested microbes, no spectrum revealed unambiguous amino acids. To leap from chemistry to biology requires extraordinary proof, and such proof remains far beyond our reach with telescopic data alone. Still, the hypothesis transforms the meaning of this encounter. 3I Atlas was not just an astronomical curiosity, but a reminder that the galaxy is chemically fertile. It whispered of the possibility that life is not isolated to Earth, nor even to one solar system, but is instead a galactic experiment repeated across billions of worlds. For those who watched its faint trace against Mars's sky, this possibility added weight to the moment. The shard was not merely passing through, it was carrying with it the echo of another world's chemistry, perhaps even the faint signature of another world's potential for life. If 3I Atlas hinted at life's ingredients, it also underscored how limited our current tools are. The observations, though ambitious, were snapshots, glimpses through narrow windows of time. To truly grasp the nature of such interstellar wanderers, humanity would need instruments purpose-built, not borrowed from other missions. And so, attention turned toward the future. The telescopes and spacecraft already planned, the machines that could transform fleeting visitors into fully characterized subjects. The Vera C. Rubin Observatory in Chile, nearing its first light, promised to be a revolution. With its vast mirror and sweeping surveys, it would scan the entire southern sky every few nights, catching faint, fast-moving objects that present instruments might miss. Where Atlas and Pan-stars found one or two interstellar travelers, Rubin could find dozens each year. Its data pipeline, automated and relentless, would ensure that humanity is no longer surprised but prepared when the next shard appears. Beyond Rubin, dedicated missions loomed. NASA's upcoming Surveyor, an infrared space telescope designed to hunt near-Earth asteroids, would also excel at spotting faint, cold visitors from beyond. Its orbit beyond Earth's heat and atmosphere would give it the clarity to detect objects invisible from the ground. Meanwhile, ESA's Comet Interceptor mission promised something unprecedented, a spacecraft waiting in ambush, ready to launch toward a newly discovered interstellar object if opportunity arose. It would be a net cast across cosmic traffic, a sentinel poised for the next arrival. Together, these tools represented a shift from reaction to anticipation. No longer would astronomers scramble after serendipitous detections. Instead, they would stand watch, systematically surveying, cataloguing, and someday approaching. Each fragment from another star would become not just a curiosity, but a sample, a data point in a growing census of galactic debris. 3I Atlas, then, was both discovery and rehearsal. It reminded humanity of what is possible, what is fleeting, and what might be achieved if we prepare. The shard near Mars was a teacher as much as a traveler, shaping the blueprints of machines not yet launched, telescopes not yet switched on, discoveries not yet made. The flyby of 3I Atlas also prompted a vision of Mars not merely as a world to be explored, but as a potential platform for observing the galaxy. Earth's atmosphere blurs and absorbs precious photons, while Earth's rotation forces astronomers to hand targets across longitudes each night. Mars, thinner in air, farther from the Sun, and already hosting orbiters and rovers, offered a tantalizing alternative. a second astronomical outpost for humanity. Imagine a telescope placed on the Martian surface, above the haze of dust, its optics trained not on the red horizon but on the black sky. From there, interstellar visitors like 3I Atlas could be tracked with clarity Earth cannot match. The longer nights, the different vantage point, the quieter background sky, all would extend the window of observation. A network of such instruments, on Earth and Mars together, could triangulate orbits with unmatched precision, watching alien fragments from two worlds instead of one. Mars-based orbiters, too, could evolve. If future missions carried cameras optimized for faint astronomy, every interstellar pass near Mars could become a natural experiment. A shard brushing the Martian neighborhood might be photographed at close range, its phase angles and geometry far superior to what Earth could ever achieve. One day, perhaps, robotic craft stationed at Mars might even deploy small interceptors, swarm probes able to close the gap and capture material from a passing visitor. For planetary scientists, this was more than speculation. The possibility underscored Mars's role as the next great frontier not only for geology and biology, but for astronomy. Our neighboring world could become a stepping stone toward a multi-planetary science infrastructure, one that does not simply look outward from Earth, but spreads its instruments across the solar system. 3I Atlas, in this vision, was a rehearsal. It showed what is lost when such a visitor cannot be reached, and what could be gained if Mars itself became part of the global observatory. The shard's silent flight across the Martian sky reminded humanity that our exploration of the universe need not be bound to Earth alone. Mars, long a dream of colonists and explorers, might also become the silent partner of astronomers, watching for the next emissary from the stars. The urgency of studying 3I Atlas also revealed the evolving culture of science itself. In past centuries, discoveries might take months or years to circulate, with data hoarded and interpretations guarded. But here, under the pressure of a fleeting interstellar visitor, collaboration became the only viable path. Observatories across the globe, operating under different nations and institutions, began to share coordinates, light curves, and spectra within hours. Preprints appeared on arXiv almost as quickly as the data were reduced, bypassing the long wait of traditional journals. This acceleration carried risks. Haste can amplify errors, and preliminary claims can ripple far beyond their evidence. Yet it also embodied the agility demanded by phenomena that refused to wait. 3I Atlas would not linger until peer review was complete. Its secrets were locked in photons arriving now, not years later. And so, science adapted, finding balance between speed and rigor, between openness and caution. Amateur astronomers too played their part. With sensitive cameras and dedicated patience, they contributed astrometric points that filled gaps left by professional telescopes. In this way, the study of 3I Atlas became both global and democratic, a mosaic of effort stitched from mountaintops, deserts, backyards, and spacecraft. The object itself cared nothing for who observed it, but its legacy would be shaped by the collective will to cooperate. This spirit echoed through the community, a reminder that the universe does not conform to grant cycles or institutional borders. Interstellar objects arrive unannounced, indifferent to our schedules. To meet them requires adaptability, humility, and trust. In chasing 3I Atlas, astronomers rehearsed the methods that will be essential for future discoveries when more visitors arrive in quick succession. Yet beneath the logistics lay something more human, the sense of shared wonder. Scientists, students, and enthusiasts alike found themselves united in awe at a shard from another star. In that unity, fleeting though it was one glimpsed the deeper purpose of science, not just to measure, but to marvel, and to do so together. When the measurements, debates, and models were gathered together, a clearer picture of 3I Atlas began to emerge, not definitive, but coherent. It was a small fragment, perhaps a few hundred meters long, irregular in form, its surface dark and reddened by cosmic rays. It bore scars of ejection and exile, tumbling through space for tens of millions of years before fate aligned its orbit with our solar system. It released no bright tail, yet hints of dust and subtle accelerations suggested it was not entirely inert. It was, above all, a survivor, an emissary of planetary processes we could only infer. The lessons it taught reached far beyond the object itself. First, it confirmed what had long been suspected, that interstellar space is not empty, but seeded with fragments cast off by alien suns. Our discovery of 3 such bodies in less than a decade hinted at an unseen multitude crossing the solar system regularly, most too faint to detect. The galaxy, then, is in constant exchange, its systems not isolated but connected by a quiet commerce of matter. Second, it reframed planetary science. Each shard represents more than curiosity. It is a probe from another laboratory, a piece of evidence that planetary systems everywhere endure chaos, collisions, and expulsions. To study 3I Atlas is to learn not only about its chemistry, but about the universality of planetary violence, the inevitability of scattering, the richness of outcomes when stars build their families of worlds. Finally, it sharpened our awareness of time. Objects like this move fast, fade quickly, and vanish forever. The window to study them is measured not in years but in weeks. Preparedness, coordination, and humility are essential if humanity is to seize the chance when the next traveler arrives. In its faint trail across Mars's orbit, 3I Atlas reminded us of the fragility of knowledge and the grandeur of possibility. We could not capture it, could not visit it, could not hold it in our hands, but we could glimpse it, measure it, imagine it, and in so doing, expand the map of what it means to be a planetary system adrift in a galaxy, alive with fragments. In the end, there was nothing more to do but watch it fade. 3I Atlas, so briefly our guest, slipped past Mars and into the deeper dark, its magnitude falling night by night until it vanished beneath the limits of our most powerful eyes. The hyperbolic arc carried it outward, past the asteroid belt, past Jupiter's distant pull, past Saturn's pale rings, until even the gas giants no longer held sway. Its path pointed toward the edge of the heliosphere, where the solar wind thins and interstellar space begins again. Astronomers marked the final observations with quiet reverence. Each data point, the last of its kind, was archived not as closure, but as a beginning, a record to be revisited when the next visitor arrives. For students and theorists, the trajectory of 3I Atlas will remain in equations and simulations, a case study in planetary science and galactic dynamics. Yet beyond the mathematics, it left something subtler, the impression of encounter, of brushing against the unknown. There was sadness in the farewell, for the object carried secrets we could not crack: its birthplace, its exact composition, the full truth of its inner structure. It withheld as much as it revealed, and yet that withholding was itself a gift. It reminded us that science thrives not on easy answers, but on questions that linger, questions that compel us to prepare better, to look harder, to wonder more deeply. As it disappeared into the distance, 3I Atlas became part of a lineage, one shard among countless others, each tracing silent arcs through the galaxy. One day another will follow, brighter, closer, perhaps within reach of spacecraft. Each will teach us more about the shared chemistry of worlds, the shared violence of creation, the shared destiny of matter cast between stars. And so, with its vanishing, the story returned to us not about the fragment itself, but about our hunger to know. The visitor passed, the data remain, and humanity was left gazing into the silence, reminded that we are not alone in the cosmos of matter, that even in the dark, other worlds leave traces in our sky. Now the story softens, the pace slows, and the words drift like dust across the last light of the visitor's trail. The frantic chase of observations, the urgency of brief nights, all recede into a calm reflection. What remains is the image of a shard, small against the immensity, moving steadily outward until it is gone. Imagine it now, shrinking to invisibility beyond the orbit of Saturn, then Neptune, then the heliopause, a tiny ember extinguished against the galactic backdrop. Its silence is complete, but not empty. For in its passing, it left us richer, with questions sharpened, with instruments tested, with imaginations awakened to the traffic of the stars. In this quiet, we can let the tension ease. The object does not threaten, it does not demand. It has simply shown itself, then departed. The lesson it carries is patience, humility, and wonder. The galaxy is full of such wanderers, and though we cannot catch them all, each reminds us that the universe is alive with exchange, that our solar system is not an island, but a port. As the narrative settles, let the thought become gentle. A shard from another star has passed by, and we have borne witness. The night sky, for all its vastness, is not empty. It is threaded with stories too faint for most eyes, yet luminous to those who look closely. And so, breathe slowly, letting the vision fade like the traveler itself. The mystery is not solved, but it is shared. The stars remain, patient and unhurried, waiting for the next emissary to arrive. Until then, the silence is not a void but a cradle, carrying both questions and peace.